Hello.
Hi, Justin. Welcome.
Hi.
Welcome.
Thanks. How are you?
Good. How are you?
Pretty good.
So let's wait a bit for people to get here.
Okay. Sounds good. Sorry, I'm just turning off some distracting notifications. Cool. Yeah. So I'm curious to hear a little bit about the group, because I've seen like discussion and so forth, but otherwise don't know much details. If while we're waiting, if you're yeah, can you tell me a little bit about all of you? Everyone's good. Hi, Daniel.
Hi, how are you?
Good.
Yeah, it's a kind of a casual study group that's open to anybody that's yeah, just interested in exploring some of the recent papers, like the breakdown paper that I've been studying that recently and thought it was very, very interesting.
Sounds awesome. Yeah, great.
Yeah.
Yeah, and thanks for having me. So yeah, I'm really I think these like linear time SNARKs are cool. I guess it's a question mark how useful they'll be in the end. But yeah, I'm glad they seem interesting to others.
Yeah, it seems like the way to go if we really want to maximize prover speed. And I guess there's just a challenge in how do we wrap it in another proof, or what sort of tricks can we use to make the size and verification time better. But yeah, that's one thing I was hoping to pick your brain about. You've probably had some ideas for that.
Yeah, and I'm happy to. There's some work in progress that I'm happy to tell you about roughly. Yeah. So I'm hoping to see some improvements soon on the proof sizes, especially. Yeah.
I think we can get started. Yeah, it looks like everyone's here. Okay, so hi everyone. So this week we're fortunate to have Justin Thaler with us, who's one of the authors of the Breakdown paper. So thanks for joining us, Justin.
Yeah, of course.
So I guess we could start if you would just like to give a sort of brief outline of the paper. I was thinking maybe we'd start with the linear time polynomial commitment scheme, and the importance of that to the paper.
Yeah, sounds good. So yeah, really the linear time polynomial commitment scheme is like, it's really the only technically new part of the paper, because other than that, we just sort of slotted into an existing polynomial IOP. And even that polynomial commitment scheme is not really new in a sense, in that like all we do really is come up with a specific error correcting code that's like actually has reasonable costs, with linear prover time asymptotically. And yeah, so that's really, the only new thing in the paper roughly is just giving that knowledge polynomial commitment scheme. There's like one other new thing in terms of a knowledge soundness analysis, but that's just like a security analysis, not new in terms of what the SNARK is actually doing. Yeah, so I guess it dates back to this paper called Lajero, which like was basically the polynomial commitment scheme we give, but using the Reed-Solomon code, which is not linear time encoding. It's quasi-linear time, and you need a FFT friendly field and so forth. And back then. There was also a paper of Jonathan Boodle and Jens Groth and others that gave the same commitment scheme, but it was a theory paper and did point out like, hey, you know, there are other codes other than Reed-Solomon that would give you linear time encoding. So we really just, you know, implement a code. That's it. Yeah, so I guess there are two nice properties. Well, you know, one is asymptotically linear time, you know, that improves over FFTs asymptotically. And then the other is it works over like any field that is at least, you know, bigger than some modest, you know, minimum size, which also is sort of an improvement over FFTs. You know, there's been some work recently on trying to get FFTs like algorithms over any field. They add like additional overheads, you know, on top of what an FFT friendly field FFT will be. Yeah, so that, I guess that's all the context. I guess one thing I will say about the polynomial IOP, I guess, is a little subtle, which is the following. How do I want to say this? I'm not aware of a univariate polynomial-based polynomial IOP that could be combined with like any polynomial commitment scheme to give a linear time prover. Like, so, you know, so our polynomial IOP that we use, which is based on the sum-check protocol, uses multivariate polynomials. You know, the popular SNARKs today, which are, you know, like STARKs, Gross 16, Marlin, Planck, they all use univariate polynomials. And basically, I don't want to say this, our polynomial commitment scheme, sort of the prover has to have in its head the evaluations of that polynomial over a certain interpolating set. So the way I think it's, they're like the coefficients of the polynomial in what's called the Lagrange basis. It's equivalent to just evaluations. And if you apply our polynomial commitment scheme to univariate polynomials, it'll like only work out nicely with linear time and all that if you use the standard monomial basis rather than the Lagrange basis. And these SNARKs, like the prover naturally has in its head evaluations, because the polynomials are defined as low degree extensions of things, which exactly means that like the prover just like is sort of handed the Lagrange basis coefficients, not the, you know, standard monomial basis coefficients. So yeah, it seems like as far as I know, the prover would have to, if you're using a univariate polynomial, do an FFT to kind of transform from the Lagrange basis to the standard monomial basis, and that would ruin the benefits of what we're doing. So it does feel like to me that multivariate polynomials are like fairly intrinsic, unless obviously people might come up with ways to modify the univariate things, but I think probably those modifications would start looking a lot like the sum-check protocol, and you'd wind up with something a lot like our SNARK. But anyway, so that's just one comment about a subtlety that's maybe a little hard to pick up on unless someone kind of points it out. And that's the end of my rambling. That's the end of my spiel. Yeah.
Do you think more generally that, say the different components of a SNARK, that multivariate polynomials or multilinearity in general is a more, say, linear approach? I mean, you can do of an interpolation, right? Mm-hmm. Is the prover time, do you think, in general, just faster using multivariates?
Yeah. It's just if you, I guess with multivariate, yeah, I don't know exactly how to answer that question, because again, I like suspect there is a way to like modify univariate things to get around the issue I just you know, discussed for several minutes. I just think those modifications are probably, you know, looking a lot like exactly the multivariate techniques today. Yeah, I don't know. If the univariate things seem to intrinsically require, if not doing a change of basis, then at least doing like a multi-point interpolation, which is like the same exact complexity. Whereas somehow with the multivariate techniques, the prover like never has to do a multi-point interpolation ever. So it's like all of the information the prover needs in its head is like is just the evaluations over the Boolean hypercube, which, the interpolation domain, which is just handed, it's like those are just the witness elements or something. And then as the protocol proceeds, like those elements just kind of get folded into each other. So there's like a collapsing of the amount of information the prover has to track. And it's like, yes, like that means that, as the rounds proceed, the prover is, essentially evaluating the polynomial that it's dealing with at more points, but those evaluations, the number is falling geometrically, and those evaluations can be obtained very efficiently from the evaluations it already knew. And so you never have anything more than an extra constant factor in prover time. Yeah, I don't know. It's like univariate. The two bottlenecks seem to be you might need a change of basis depending on the polynomial commitment scheme used, and you might need a multi-point interpolation. And it just seems very hard to avoid that.
Thanks.
I have a question regarding, error-correcting codes and polynomial commitments, or multilinear polynomial commitments. Can you explain a bit of the intuition behind how one gives the other, and like how does the properties of the error-correcting codes relate to properties of the commitment scheme?
Yeah, okay. Well, the second one is easier than the first, which is, okay, so the prover time in the SNARK is like totally determined by the encoding time of the code. So, the faster the code, to go from like a message to a code word, the code word encoding the message, the faster the prover will be in the SNARK. The proof size and verification costs are mainly determined by the distance of the code. Let's see, what other properties of the code matter? And the prover space is determined by like the size of code words, because basically all the prover does is like store a bunch of code words. Yeah, so that's how like the code translates to SNARK costs. Yeah, so encoding time is like prover time, distance is going to give you the verifier's cost, and code word size is prover space. In terms of intuition, it's a little harder to say. Let me think. If people are familiar with Fry already, it's actually like kind of the same intuition as Fry. Fry like repeatedly does folding, like, so the prover takes the polynomial to be committed. It's a univariate one, and it evaluates it over some multiplicative subgroup. So that's that multi-point interpolation, if the prover is honest, right? And then it starts interacting with the verifier to, it repeatedly folds the committed vector in half, so it kind of takes a random linear combination of the first half and the second half to half the size of the vector, and then does it again and again and again. So the commitment scheme in Brakedown really just does one giant fold where it kind of, rather than having one big vector that you fold sort of in half logarithmically many times, it has root n smaller vectors that it just does one big fold of. Okay, so like in Fry, the reason the folding kind of works is it uses the distance property of the Reed-Solomon code. Like that is, the big vector is a Reed-Solomon encoding, and kind of if the prover started with a lie, kind of with high probability over like the verifiers picking the randomness to use in the fold, after the folding, it will still be left with a lie, and how detectable, how big is the lie is like related to the distance of the code. So it's the same thing here. So there's nothing really special about the Reed-Solomon code in the intuition, I just described Fry with. That said, there's actually an open question I'd like to answer, which is kind of to do Fry, but with arbitrary, with a linear time encodable code. So as an asymptotic question, if you're willing to use SNARK composition, it's it's sort of done. As soon as you get square root verification costs, you know, you can compose a square root verification cost snark with itself once, and the costs go down to end of the 1/4, and then you compose again, and it's, you know, end of the 1/8 or, you know, 1/16, and you can just keep reducing the cost through composition. But if you don't want to use composition, we don't know like a log round variant of breakdown with like polylogarithmic like verification costs without going through snark composition. And what this paper by Buru, Chiesa, and Groth was able to get sort of constant round. So they generalized, you know, this the commitment scheme in Breakdown, you know, in Lahera, you know, these prior works. They generalized it from like one big fold to like a constant number of folds, but there's a cost that grows exponential. It's like the distance of the code to the number of folds. So it's like the verification cost if you do like T folds is something like distance to the T times polynomial size to the 1/T. Anyway, so the message in practice is like I worked it out. It seems like doing more than one fold is actually concretely worse for you, both because anyway, they're like just nasty costs that grow exponentially with the number of folds. So yeah, we don't know a Fry-like protocol with a linear time encodable code. And as far as I can tell, the issue has something to do with like I don't know, like tensor structure in like the I don't know, like the multiplicative subgroup that, you know, the interpolation set for Fry is defined over. So there's just some extra tensor structure with the Reed-Solomon code that like isn't there somewhere with these linear time encodable codes. I don't really have a very precise sense of what that, you know, exactly how to formalize what I just said, but yeah, so that's open still.
I think the paper mentioned there is an option to use a higher degree tensor code to get better succinctness, but is that different from the technique you just mentioned, this other paper?
Higher degree tensor codes. I think that so I don't know what remark you're referring to, but that does sound like basically what BCG did. Maybe I mentioned that. Okay, I think we did mention that in open questions, which was basically, you know, we had thought about implementing like BCG, but decided that it would actually be of worse cost for the reasons I said. There's some like nasty dependence on the number of folds that overwhelms the benefit of doing more than one fold. So I think we just mentioned like, you know, well, maybe we're wrong, or maybe there's some way to, you know, improve BCG. So you would get something, you know, more practically interesting out of it. Yeah, I think.
Yeah, the paper mentioned you can get a proof size that's proportional to the Tth root.
Yeah, that must be what it's saying. Yeah. And you can't take T all the way to log n, like even asymptotically, because there's some costs that grow exponentially with T. So once T is log n, those are like polynomial costs, and they really matter. But when T is constant, you know, like a constant to a constant asymptotically doesn't matter, but concretely does. Yeah.
Those costs, is that because we're sort of applying the code in T dimensions now, and then the blow up grows with the number of dimensions? Or
yeah, so what's happening there? Okay, so maybe I don't know if this intuition is exactly right, but what BCG use a tensor code, right? So if they would like, if they want to do two folds, they would take like the breakdown code, say, and tensor it with itself once. Okay. And the problem with that concretely is the distance of that tensor code is quadratically worse. It's literally the distance of the original code squared. Actually, okay, so I'm going to mention now some work in progress, which is I think we have new, different linear time encodable codes that have like much nicer distance than Breakdown's code for the same like encoding time. Like basically everything else is the same and just the distance is better. And the distance seems to be, so my postdoc is like grinding through some nasty calculations to try to like formally analyze the distance, but he thinks the distance is actually going to be like almost as good as the Reed-Solomon code, which is like, you know, best distance possible. Actually, something interesting, I keep going off on tangents, is you can actually conjecture, all you need out of these codes is not that they have good statistical minimum distance. There can exist close code words as long as it's intractable for a cheating prover to find them. So you can actually conjecture that like these codes we're proposing have, you know, computational minimum distance. People call it pseudo distance, actually beyond 1 minus the rate. You know, I don't know if how comfortable people would be with that conjecture, but you could do it. That's like very powerful. And if you had that, you could use the tensor code, because squaring, you know, something very close to 1 is okay. Basically, doesn't really make a big deal. But in Breakdown, the distance we showed was like 1/20th. So like you square that, it's you know, it's 1/400. It's just not going to give you anything. So we just wrote off the BCG approach there. So yeah, we should revisit it actually, with if we get the better codes to work out.
I was actually going to ask about BCG as well, but I think you discussed that at some length. I was wondering if you've also compared it with, you know, there's a way of taking univariate Fry and sort of, you know, you commit to a univariate polynomial and then you end up with, well, once you Fry it, you get the multilinear thing.
Mm-hmm.
Are you familiar with it, and have you compared it?
Compared it. So you're saying, have we compared like Breakdown to this multilinear version of Fry? Like taking Fry and turn it from a univariate to a multilinear one. So we compared directly in the Breakdown paper to Fry itself, where we say like a degree X univariate polynomial, you know, is like equivalent to a multilinear polynomial with log X variables, right? Like the number of coefficients are the same. So that transformation would only add more overhead, would make the Fry approach like more expensive. So yeah, I don't know. I don't have a great sense off the top of my head exactly how much more expensive it would be. I think it would, you know, depending on what transformation you use, there you might be referring to transformation in the Gemini paper. Maybe they gave a transformation. And then I think Hyperplonk just updated their paper to, you know, point out Gemini uses KZG, and Hyperplonk now has said, oh, let's swap out KZG for Fry. Anyway, I think that would roughly double the cost of Fry. I think you're basically running Fry like once for the univariate thing, and then roughly once, I think, in the transformation. Like the transformation itself looks a lot like Fry, but don't quote me on that. And anyway, so if you look at just the section of Breakdown that just looks at polynomial commitment schemes, we compare to Fry, and like that's an optimistic comparison for your question. Optimistic in terms of you know, giving the Fry stuff like, you know, the advantage. Yeah.
I was wondering how you would think about this code in the context of like the Spielman code and the generalization that Orion uses. If you could please give a high-level comparison.
Yeah, sure. Okay, so Spielman's old work really wanted two things that we don't care about at all. So one, well, I shouldn't say at all, but we almost don't care about. So one is fast decoding. Okay, and for us, no one ever has to decode. If we did have fast decoding, we would our knowledge extractor would be nicer, a little nicer. But anyway, let's just ignore that because that's, you know, in the security analysis, not in the actual SNARK performance. So yeah, so we don't need fast decoding. Spielman wanted that. And we're also happy to work over pretty big fields, but like the coding theory people don't want to work, you know, a big field to them is like, I think, you know, a field with 128 elements or something is like really big for them. So we kind of just take something like Spielman's construction and like simplify it because we just don't care about a bunch of things he cared about. I mean, I would just say it's that, and then like, you know, pay attention to constants and stuff. Whereas he didn't care about constants. So we do some, you know, optimizing parameters, and it's really just that. Does that make sense?
Yeah. And just drilling in a bit more, I think there's like a couple main differences.
Mm-hmm.
One being that I think in the general Spielman code, there's this like expander matrix, at least the way Orion uses it, there's this expander matrix that's used kind of twice. Once for shrinking the input, and then again for sort of expanding the recursively encoded input. And yeah, I thought it was really interesting how Brakedown only uses an expander once. At least this is how I interpreted it.
Yeah, no, I think we do it. We do exactly what you just described.
Well, I think if I understood correctly, the sort of shrinking matrix or compression matrix in Brakedown, it doesn't really need an expansion property. It just needs the property that low weight inputs won't be mapped to 0.
Yeah, okay. I think that is true, but I think like proving that goes through an expansion property, I think. Or something very expansion-like, at least.
Yeah. Yeah, I guess it ends up being similar, but I think it is concretely a bit better, the density of that matrix with that weaker property.
Yeah. Okay. So I guess I'll have to look at like what Orion is doing in more detail offline, I suppose, to say more. I mean, oh yeah. So Orion, I mean, I guess you know they say it in the paper. So their main goal was to get the probability that the code fails to satisfy the requisite distance bound lower, because they didn't like the asymptotic statement that like in Brakedown it's 1 over like n to a constant, but the constant's like really big. So concretely, you know, it's like we set it to 2 to the minus 100, and our analysis is like almost certainly like not remotely tight. And also, even if the minimum distance fails, the prover would actually have to find close code words to attack it. And I think it's actually very reasonable to think that that's not tractable. But anyway, so yeah, so what they wound up doing was they kind of gave a procedure for, roughly speaking, I guess, like taking one of randomly generated code and kind of detecting if it fails to satisfy the requisite distance property. And they do a good enough check that they get that failure probability down to, you know, inverse super polynomial. Yeah, so it's possible that they had to modify the code a little bit to just make that analysis of their, you know, checking procedure work out. And that's actually that's my guess for what's going on, because their checking procedure checks for, you know, some kind of small set expansion property. So it would sort of make sense that they would, you know, be looking at actual expansion all the way through, you know, their graph construction, given that their checking procedure is checking expansion. Did that make some sense?
Yeah, I think so. And then I guess the other difference is that classically we use sort of this unweighted expander graph, and Brakedown uses this matrix with random weights, which I guess we can think of as like a weighted bipartite expander graph. Yeah, I wonder, do you think that leads to better sparsity if we use this random weights instead of just 0 and 1 weights?
So I guess the Brakedown construction uses random weights, right? So we sort of did the best we could with that. And yeah, I don't think we could have done as well if we were using 0, 1 weights. So so I guess the answer is yes. We do have sparser expanders, I believe, because we have like random field elements as the weights, and the fields are pretty big, right? So
Yeah.
that's like a nice injection of extra randomness there, I would say.
I was also wondering, do you see any major issues with using this with smaller fields? I know there's some analysis that depends on the field size with these matrices that you choose, but yeah, so we probably need to play around with the numbers, but besides that, do you see any major issues?
Yeah, so I'm pretty optimistic about this. Like stepped on the power cord. My postdoc, like the numbers he is seeing right now, again, like everything could break in his analysis, but like the concrete numbers for small field sizes seem like pretty nice, and he still doesn't think his analysis is tight. So I think for like 60-bit fields, with the same encoding time that we're seeing in Brakedown, he's seeing like, the distance being all the way up at like 2/3 or something. So, whereas Brakedown's like 1/20th. I think he's seeing like a failure probability of like 2 to the minus 50 or something. And, that's like a, once for all time statistical failure probability. It's not, some computational security parameter. So I am pretty optimistic that, you should be able to go down to like 50-bit fields and make everything work out. You're just going to have to, everyone's going to have to decide, like what is a failure probability for the code, being crappy that they're willing to tolerate. And, to repeat like over and over again, it's not enough just, for there to be an actual attack. The code actually, the distance analysis could actually fail. But if close code words are hard to find, because these are randomly generated codes, then the thing is still secure. It's just, it will be based on a computational conjecture that close code words are hard to find. Anyway, so those are all my thoughts, I guess, on that. So I do think it should be pretty good for small fields in the end.
Yeah. And also just wondering, like, do we, if we sort of trust the setup, like if we, trust that the person who publishes the randomness or whatnot for the code isn't trying to create a bad code, then does that mean maybe we don't need such a small soundness error? Maybe we can do 2 to the minus 20 or something like that.
Yeah, so it's an interesting question. So I think you can basically, it's a transparent setup, right? Like in practice, you would just have like a PRG with some seed, like, I don't know, the first sentence in Shakespeare's play or, whatever. And the PRG would like generate the random, encoding matrix for you. So it's effectively like, you can trust that it was generated at computationally at random, right? The only question is, might there be an adversary who can like, within their resources, like find close code words, but like no one else in the world can even detect that there exist close code words. That's what it would take to attack this code, in the sense that if anyone in the world is able to like find 2 close code words in this code, they can tell the world that and say, hey, we got unlucky. This thing isn't secure, like let's regenerate the code. We'd have to get unlucky again. And for the adversary to attack the thing, it'd have to actually find the close code words itself, right? So like the attack would strictly need like more resources somehow than like anyone in the world who might decide to, try to do their best to check the code for safety. Does that make sense?
Yeah, I think so. Thanks.
So yeah, so I mean that feels like a pretty good trust model for me to like set that probability, like, I don't know. Yeah, I mean, the attacker could be like the US government, and they actually will have more resources than everyone in the world or something. So you don't want to take that too far in terms of, trusting that the attacker isn't going to be strictly more powerful than literally everyone who wants to use the SNARK in the world or whatever. But yeah.
Is there an analogous way to, in Fry, you can just query multiple times, and then you kind of suss out the errors generally. Can you decrease the soundness error by any sort of similar trick here?
Yeah, yes, and that's another. So there's a very similar sort of trade-off between security and verifier costs for breakdowns polynomial commitment as with Fry, and it's because they're both based on like essentially the same techniques in terms of error correcting codes and Merkle hashing. So you can always just increase verification costs, just do more in breakdown, and the verifier would do more column openings. In Fry, it'd be more what they call Fry verify queries, and drive the security better. And that's also another point to make about the code kind of not being good is it's not some binary thing, I don't think, where it's not necessarily some binary thing. I don't have the full analysis cached in my head to say, there's probably one like bad event that dominates the failure probability. And if that bad event happens, then like the distance is like not very good. But I think not very good is not like, the end of the world bad. So like you could just like really, jack up the verification costs, like literally like assume that bad event happens. So the distance is like not very good. And it would still be secure if you made like way more verifier queries. In a SNARK, I guess, unfortunately, you have to tell the prover like how many queries it should be providing. I think that's right. Yeah, I mean, I guess you could sort of imagine like the SNARK. You make the SNARK big, it has like, extra verification queries in there to be really, really conservative on security. But then the verifier only like verifies as many as it, takes for it to feel comfortable. And you save some on verifier time, but you don't save any on just, proof length. I don't know, you could imagine something like that. Yeah, sorry to go like in 10 different directions in that answer. Let me know if that wasn't clear enough.
Yeah, I think that makes sense. Yeah, I was also thinking about the folding, like having one big fold in terms of distance is, maybe it's just my lack of intuition, and when you fold and you get this nice logarithmic thing, it kind of intuitively makes sense that you have it so that the distance is like roughly preserved. When you do this one big fold, it's difficult for me to see how independently of the size of the code you would get sort of the constant guarantees.
Okay, I think the best I can say is the following: like all of these papers, Fry, Ligero, Breakdown, all of them using these code-based polynomial commitments. Like the key lemma in the analysis is the following. It roughly says, if you have a bunch of vectors and you take a random linear combination of them, then if even one of the vectors you're taking random linear combination of is like far from your code, like far from being a code word, then unless you get really unlucky in the randomness in the random linear combination, like the linear combination will also be like just as far from the code. It doesn't matter how many vectors you're taking a linear combination of. I guess the intuition there is like even one bad apple is enough to spoil the batch. So, if you have a million bad apples or a million apples with one bad, it's just as bad as, having two apples with one bad. And then, yeah, so Fry just like logarithmically many times applies this sort of thing to two vectors that it takes a random linear combination of. Whereas, Ligero, Breakdown, all the others applies it once, but to more than two. So I think that's the best I can say.
Yeah, that was a great explanation. Thank you.
Yeah, I have a small question actually. For the paper itself, I have some thing cannot totally understand. Actually, it's the first sentence of the whole paper. It's like
Okay.
in the introduction part. It mentions that the size of the pi and the cost to verify it are both sublinear in the size of the weightness. So I'm here curious about why it's weightness, because usually I remember Damani mentioned that usually SNARK is like logarithmic to the size of the number of gates of the circuit.
Yeah.
So
yeah, so great question. I guess I'll start by saying, like, people use succinct, and different people use it in different ways, and no doubt it really annoys some people how I use it. So some people use it to mean like log costs for the verifier, or even constant number of like group elements or something. I like to use it for like anything that's non-trivial. So anything smaller than like the NP witness is non-trivial. So that's what I use succinct for. And I would use like strongly succinct or something for one of the other notions. Okay, so now in terms of so your question is like, should square root circuit size count as succinct? And what I would say there is the following. So we describe breakdown for R1CS, and for R1CS, the NP witness is like the entire, R1CS solution, and our proof length and verifier costs are square root of that. So I think it is fair to say, for R1CS, we are succinct by my definition. Now, if you were to apply breakdown to circuit sat instead of R1CS, which you could do with like kind of, straightforward modifications, now it's possible that the witness is smaller than the whole circuit, like asymptotically smaller or something, and then square root of circuit size would not be succinct, and yeah, it would not be succinct. I would say that it seems to happen like very infrequently that you have an application where it like naturally turns into like a nice circuit, and the witness to that circuit is like, sufficiently small that this is relevant and we wouldn't be succinct. And in that case, what I would say is you should apply a GKR protocol based SNARK. So this is an interactive proof for like circuit evaluation. Anyway, the SNARKs based on this protocol only apply the polynomial commitment scheme to the circuit witness. Okay, so you can, and in that way, whatever the cost of the polynomial commitment scheme are, only get applied to the circuit witness and not to the whole circuit. And then we would be succinct by, any definition. Yeah, so that's my answer to that, I guess. Does that make sense?
Yeah, cool. Thank you.
Yeah, so you just swap out the polynomial IOP for like a different one, and that ensures the polynomial commitment is only applied to the witness to the circuit.
Yeah, that's true. Cool.
Any more questions?
So building on that, do you have any concrete applications in mind where you think this would be the ideal fit, either the PCS itself or the entire SNARK?
Yeah. Okay, let me think. So in general, I'm like, bullish on some check protocol based SNARKs, which is, I'm very open about that. One thing I really like about some check based SNARK, so this almost has nothing to do with breakdown other than our polynomial IOP is some check based, is that for certain problems, you can get what I call a super efficient prover, where the prover just like solves the problem with the fastest known algorithm with like, forget about proving correctness, and then does like a low order amount of extra work to compute the proof of correctness. And you, as far as I know, and I'm like pretty confident that that like this is unique to some check protocol based stuff. So that's one reason I'm excited about some check based SNARKs. In terms of the breakdown polynomial commitment, like even today, where there's been a bunch of follow-up works, Orion, Hyperplonk, part of Hyperplonk was trying to improve breakdown to get the proof size down. There's something out of consensus called Vortex, which was bringing in lattice-based techniques on top of like the sort of the breakdown approach. None of those are field agnostic. Breakdown's still the only one that's field agnostic. So one thing, if you have some weird field, this really might be like your only choice, especially if the field is pretty small, because look, you could actually, the elliptic curve based stuff, especially the pairing free stuff like bulletproofs or something, like you almost always, if your field is big enough, like could cook up a curve that, discrete log is probably intractable over that curve and get something, resembling field agnosticism there. But A, that needs like a pretty big field, for your curve to be secure. And B, you're like cooking up a new curve all the time, and that's like annoying and stuff. Yeah, so field agnosticism, if that's important, today, if you wanted to prove something about the Bitcoin curve, it's not FFT friendly. So, what would you do? I don't know what you would do other than use something based on breakdown. And then I guess the last thing is, the linear time stuff does matter for like proving like basically committing to like really, really, really big polynomials. So Daniel and I think talked about on Twitter, like, will anyone ever really want to do that? Yeah, I think there's a lot of room for maybe different viewpoints on that. If recursive composition like just takes over the world, you kind of never have to apply a polynomial commitment scheme to anything particularly big, because you just break everything up into small pieces and then kind of recurse. But if it, that's not the only way necessarily you could think about doing things. So it does have some overheads and blah, blah, blah. So yeah, I guess those are my thoughts on where this would actually be useful.
Thanks.
Yeah, about the field choice, one of the fields we're really thinking about is the 31-bit Mersenne field, which would work very nicely with CPUs and GPUs, since GPUs only support 32-bit multiplication and CPUs support 32-bit vector multiplication usually. So yeah, it's very nice just having the flexibility to use choices like that, which we couldn't really use that with Fry. We would have to use complex roots with our FFTs. So I think that probably wouldn't work very well, but it might work really well with something like Breakdown.
Yeah, I think that's right. I just start to worry about the code distance failure probability analysis when the fields are that small. Like yeah, I'd definitely be worried about that, but I'm not convinced that it's actually too high a failure probability, or even if it is somewhat high, there might be like an Orion like algorithm to start checking for the failure and then just regenerate or something. So yeah, I think that could be right, which would be nice. So there is definitely a failure probability of 1 over message length, but our message length is square root of circuit size or R1CS size or something. So I think there's as far as I know, there's no way around that source of failure, but like that's not going to be big enough. Like it's fine. Sorry, your field, a 32-bit field is big enough that square root R1CS size over 2 to the 32 or something is okay. Like that's still pretty small, just not cryptographically small. Yeah. So yeah, that's helpful to know about. That'd be cool.
I had one last question. If we're committing to a batch of polynomials, do you think there are any clever ways to do that, or just kind of besides just putting them in the same Merkle tree?
Yeah, my initial instinct, because I haven't actually thought about this that carefully, so I should. My instinct, so don't quote me on this, is everything should be hopefully comparable to Fry. So basically, it's not homomorphic, so you don't get like as good batching properties as with like KZG and bulletproofs and what have you. But there is still non-trivial amortization that you can do. And I guess all these Fry-based projects, I think, are doing that, since you do commit to a bunch of polynomials, like one per column of the, however you're interpreting the NP witness as several columns. And yeah, so I would guess you can do something analogous for this. So let me say, I don't know, I is 70% sure, just have to go through the details to confirm. Does that make sense?
Yeah, I'll need to think about that some more, but I think that makes sense. Thanks.
Yeah, I think maybe I can think through this through online. So with Fry, if you want to do this batching, like you can, so I break Fry into like a commit phase, like a folding phase and a query phase. People lump the first two together and just call it the commit phase. So obviously there's no way around what I'm calling the commit phase. Like you have to, compute the Merkle hash that is the commitment. It's just one Merkle root. So if you're committing to 20 polynomials, you have to do that for each polynomial. And if the polynomials are big, like that will be sort of the prover bottleneck, but if, one is FFT, the bottleneck, that's where the FFT happens, right? So if they're not that big, FFT, won't be the bottleneck. Then you do the folding phase, which query, the proof is coming from. Sorry. Okay, I can't do it online. Sorry. I thought I could do it within 20 seconds of thinking. I need more time. Yeah. Anyway, so Brakedown also proceeds in like a commit phase, testing phase, and query phase. So it should be the same sort of thing. At least one of the phases, you should be able to kind of amortize the cost across all the polynomials. I think that's what happens with Fry, and I think the same thing should be going on here. So like if that phase is the dominant cost for prover or verifier, like the batching should be really helping you. And if it's not the dominant cost for either, then it doesn't really matter too much.
Yeah, usually with Fry, we have sort of a special fold in the very first fold where we don't really, we're just combining a batch into a single point using randomness. So yeah, maybe there's something similar we can do there, but I'll need to think through that.
Yeah. Okay. Yeah. So I'm probably just going to waste everyone's time if I try to say anything else. So yeah, that sounds right. That sounds right.
Maybe slightly off topic. Well, it is slightly off topic, but you seem a bit hesitant about recursive proof composition for code-based SNARKs. Can you expand on your worries there?
Yeah, I mean, I don't know exactly how. I don't want to overstate my worry, but I think so. There's sort of two worries. So one worry is just if we want like sort of I don't know, legacy industry to use this technology, whether it's because they're getting into blockchain, crypto, Web3, whatever, or just forget about that application domain and just there are applications of SNARKs that you can easily think up in non-blockchain settings. They just tend to be very conservative with the cryptography they adopt. So with like totally heuristic security, in the sense that it's random oracle model, but then like you really you start with that, but then to do recursion, you really do have to instantiate the random oracle, like as a circuit, right? So there, it's just completely heuristic, right? You don't even wind up with security in the random oracle model in the end. I do think that might be a problem for just getting adoption of the conservative entities. In terms of whether there might actually be attacks that are non-trivial, I mean, I would guess there aren't, but it just wouldn't be a super high confidence statement. And this is just one thing that leads to this is, so, this BCG paper and it's follow-up BCL. So Boudou-Chiesa growth, Boudou-Chiesa Lu. Like their results are trivial if you allow SNARK recursion. You know, right? Because like dating all the way back to, you know, the 2017 paper of like Boudou and Groth, we like asymptotically had breakdown already, you know, like you just do the one fold and you use a linear time encodable code with constant rate and distance, which we already had, they just were impractical. And then that gives you like the, you know, a SNARK with square root verifier cost linear time prover. So just recurse, you know, recursive with itself, right? So kind of the whole point of Boudou-Chiesa growth and then BCL after it is to avoid SNARK recursion. So if SNARK recursion like is just generically secure, you should just rip those papers up. Like there's no point to them. And I just kind of hesitate to say there's no point to those papers. It just feels like, you know, just follow what those papers just feel very natural and nice. So it's just hard for me to, it's like, you know, recursion just is super powerful. It lets you just avoid, you know, entire Eurocrypt papers. So yeah, it's hard for me to say. You know, and if every level of composition sort of makes you lose one bit of security, like this can matter if the composition goes pretty deep, which you know is going to happen more and more. And like, you know, something like Mina is like every block of the blockchain or something has another level of composition. So it doesn't take much of a non-trivial attack for the non-triviality to become, you know, a complete break. So that's, I guess, another thing to say.
So, but that's slightly different though. I mean, Mina uses Halo, right? They use an elliptic curve sub. So that's separate from the code.
Okay, so the whole instantiating the random oracle, so losing random oracle security thing happens whenever you use fiat Shamir, and Halo 2 is doing bulletproofs. Halo was KZG. Okay, so if they're recursing KZG, I agree, you don't need fiat Shamir. So what I'm saying goes away. It's still possible though that so it's no longer heuristic security, but for the fact that you know, our knowledge extraction procedures grow exponentially with the depth of the composition. So it is still heuristic, even, you know, just because they're doing deep compositions. You know, yeah, with given what they're doing. If they do depth 2 composition or what, you know, small depth composition, then I agree. You know, up to exactly the concrete security level, it's fine. You know, like if Halo is a SNARK, then it's fine to compose it with itself a few times like that, you know, and if it's not a SNARK, then it doesn't matter if you're composing it with itself or not, it's not secure. So yeah, I do agree with that. Let me just think if there was one more comment. Okay, so and then the last thing I'll just point out, just in case anyone here is not aware, it's well known that this random oracle methodology where you know prove something secure in the random oracle model and then, you know, instantiate the random oracle with a concrete hash function. It's known it's not secure. It's just the things that it's known to not be secure for are like wildly contrived, where the statements that, you know, you can forge a false proof for like refer to the hash function that you're instantiating the random oracle with or something like that. Which is maybe not like that wild because, you know, if your hash function is SHA, then people do want to prove statements about SHA all the time. So that is definitely like a reason to be a little bit cautious with composition where you know, it's really heavily relying on instantiating that random oracle, like just more heavily than without composition when we do have security in the random oracle model, you know, for the end-to-end protocol and then just instantiate the random oracle kind of at the end. Yeah, okay, that's all my ramblings on it.
I think this is really interesting. It should be formalized into a paper by someone, some, you know, recursive SNARK cryptanalysis.
Yeah, I guess the thing is, like, everything I said is like known, but I guess it'd be okay. It feels like a good blog post maybe to synthesize what's known and maybe offer some of the subjective commentary I did. So maybe, yeah, maybe I'll do that. I'll write a blog post. Yeah.
Yeah, actually, I'm also wondering if there are any, let's say, theoretical bound for the depth of the recursive.
Yeah, so what's happening is, okay, so here's a little more detail about the security analyses.
Yeah.
Okay, well, firstly, let me just say, regardless of the depth of the recursion, there are no non-trivial attacks known, which means the trivial attack is, if you prove that you know a proof, 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 blah, 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 blah. The best known attack is to just like, in your head, go through, I don't know, basically to like forge, that first proof, like to basically, break like one atomic invocation of the SNARK. Okay, but we can't, the security analysis, roughly what they don't rule out that there's some way to kind of produce a convincing proof of the final statement, like without in your head producing, accepting SNARK proofs all the way down. There might be like a shortcut, that a cheating prover could take. And okay, what else do I want to say? So the knowns, yeah. Okay, so the current, deployments of recursive SNARKs, they kind of just assume that there's like basically the known attack is completely optimal. And then the security analyses, like what they have this exponential loss in the runtime of the knowledge extractor. And I can be a little more precise about what that exponential loss is. So normally security knowledge soundness is proven invoking some kind of forking lemma, which means the knowledge extractor will like run the prover to completion to hopefully get like a valid, like an accepting proof, and then rewind it a little bit and like run it again with like fresh verifier challenges and get another accepting proof, and then like rewind it again. And kind of the number of times it has to rewind and restart the prover. I don't know, let's call that A. Basically the knowledge extractor for the, depth decomposition will actually have to run the prover it's extracting from like A to the D times. Okay. And yeah, so even depth 1 composition, like that's a major loss in security concretely, because you're losing a factor like 2 in the exponent of the runtime, something like that. Anyway, that people are just sort of assuming like that loss is some artifact of our security analyses right now, which it may well be. So the one thing I will say, like in favor of deep recursion, I guess, is the following. So, the code-based SNARKs based on Fry and Brakedown and all these code-based polynomial commitment schemes. There is actually, in the random oracle model, there is an extractor for them that's straight line, meaning A is 1. Okay, meaning there's no rewinding of the prover. Okay. So that means like if you're really, really like take your belief in the validity of the random oracle paradigm like to an extreme and like really think an adversary can never treat like SHA-256 as anything but a random oracle, then there should actually be like almost no loss in security, regardless of how deep you go, as far as I know. But like, yeah, we know that like the random oracle paradigm like doesn't work in general. We just so the question is, how extreme do you want to be with this so this straight line extractor, what it does is like while the prover, the adversary, is like searching for a valid SNARK proof of a false statement, it has to be querying the random oracle, over and over again as it's searching for the proof. And this knowledge extractor just like watches those queries. And somewhere in those queries must live like basically an NP witness for the statement, essentially, unless it like, finds a collision in the random oracle, which, you can basically assume it never does because it would take so many queries or whatever. Yeah, so if any, if you're ever trying to attack one of these composed SNARKs, which I think, people should try, everyone should know, like, if the composed SNARK like uses Fry or something, you are fundamentally going to have to treat, with the hash function you're using to do fiat Shamir or whatever, not as a random oracle. And we do not know attacks that do that, except in very contrived settings. So I'm worried we just like won't get anywhere either way. Like we won't, because the attacks have to treat the hash function not as a random oracle, we might not have better attacks, but we also might not make any progress on better security proofs. So then we're just stuck. I don't know.
A random follow-up to that. So I think for KZG based SNARKs at least, if you want to get like full conclusive security, you have to assume AGM or algebraic group model, right? So and in that case, the structure is straight line. You don't need to use forking lemma, and you don't incur the loss as you recurse, right?
Yeah.
And I think for some of those SNARKs, you have to assume the AGM to even get any security.
Yeah. Yeah. So and so this whole, I guess, like believing in the random oracle methodology is like in very much the spirit of believing in the algebraic group methodology, right? Like we do know that there are attacks that don't work in the algebraic group model. I'm not versed in what those attacks are, and I assume that they're apply in sufficiently contrived settings that it's the same exact situation. People just think for the protocols people actually use, like KZG commitments, those sorts of attacks just don't help. Yeah, so it's the same kind of situation there. I agree. I think the difference is okay. Okay, so I think you can make like very, very, very strong assumptions about the efficiency of the extractor that the algebraic group model posits the existence of, and also get this situation where there is minimal security loss, like concrete security loss, or even asymptotic with depth. But actually, it's like pretty hard for me to believe, and I'm not the main person that should be speculating on this just based on my background. But I'll just, in my like non-expert opinion or whatever, it's hard for me to believe that there is an extractor that will take like some entity that attacks KZG or whatever, and pulls like the coefficients of the polynomial like out of its head in like a straight line way, without like running it even twice or something, right? And as soon as that thing is like run, the adversary, the extractor is running it twice, you have this exponential loss with the depth. I mean, you can go to log depth if it only runs it twice. You can't go to log depth if it runs it polynomially many times. Yeah, so I guess that's I have no idea what that kind of extractor would look like.
It's kind of like a magic black box equals to AGM, right? Because one group element can give you a list of, the representation in terms of the elements that average you have seen. So, which is definitely a
so it's like it's a little weird. It's like with the random oracle model, I do know what the extractor looks like. It just watches the the random oracle queries, which in practice would mean like looking at what inputs the adversary is evaluating the hash function at. Whereas with the AGM, the model doesn't have the adversary making like queries, I don't think, that you can watch. It just posits an extractor. So, and that feels like a different flavor to me. Again, I do feel a little uncomfortable discussing in great detail the relationship between random oracle model and AGM, and like how they're alike and not alike, just because I really haven't done very much with AGM at all, but that's my understanding. Cool. Okay, any last questions?
Okay, if there's no more questions, I'd just like to thank you